Welcome back, knowledge adventurers. You've tuned into the All Sorts podcast, your one-stop shop for diving deep into the most fascinating topics.
That's right. And today, we're taking you on a journey into the fascinating world of information theory.
Oh yeah, information theory. It sounds kind of complex, right? Like something only mathematicians would understand.
Well, it does involve some math, but the beauty of it is that the core ideas are surprisingly simple and elegant.
I like simple and elegant. So what exactly is information theory about?
At its heart, it's about using probabilities to understand and measure information itself. Like, how much information is there in a message, or how much uncertainty do we have about something?
Okay, I'm intrigued already. But before we get too deep, let's make sure everyone knows where we're getting our information from today.
Right. Excellent point. We've got some great sources for this deep dive. We've got excerpts from Wikipedia's Entropy Information Theory page, a great overview from Science Direct Topics called Information Theory and Overview, a really accessible explanation from Study Smarter titled Information Theory, Basics and Applications. And then we've got a bit more of a formal treatment from a PDF document simply titled parta.a.pdf.
So we've got a good mix of sources to draw from. All right, so what's our mission today? What are the key things we want to uncover during this deep dive?
Well, the first thing is to really grasp those core concepts of information theory. We're talking about things like information content, surprisal, and of course the big one, entropy.
Entropy, that's a word that gets thrown around a lot, but I have to admit, I'm not always sure I fully understand it.
Don't worry, we'll break it down. And then once we have a solid foundation, we'll explore some of the surprising applications of these concepts.
Applications? Like how is this stuff used in the real world?
Oh, in so many ways. From data compression and communication to cryptography, machine learning, and even statistical physics. It's a truly foundational theory with its fingers in a lot of pies, so to speak.
Wow. Okay, I'm officially excited. Let's get this deep dive started. So when we talk about information in this context, what are we really talking about? It seems like such an abstract concept. How do we even begin to measure it?
That's a great question. And that's where the idea of information content or surprisal comes in. It's a way to quantify how much information we gain from an event. The basic idea is this: the more unlikely an event is, the more surprising it is when it happens, and the more information it conveys.
So like if I told you the sun rose this morning, you wouldn't be very surprised. That's a highly probable event, so it doesn't carry much information.
Exactly. But if I told you it snowed in July here, that would be pretty surprising, right?
Yeah, that would be huge news. Because it's so unlikely to happen.
Precisely. And that's reflected in the information content. We can actually calculate this information content using a simple formula. It involves something called a logarithm, but don't worry too much about the math for now.
Okay, as long as we don't have to solve any equations, I'm good.
No equations, I promise. Just think of it this way. A rarer event, something with a low probability, will have a higher information content, and a common event will have a lower information content.
Makes sense. So the less likely something is, the more we learn when it actually happens.
Right. It gives us more new information. The Wikipedia article on entropy information theory points out that this use of the logarithm isn't just random, it's actually the only mathematical function that fits the bill for measuring surprisal.
Ah, so it's not just some arbitrary choice. There's a deeper reason behind it.
Precisely. There's a kind of mathematical elegance to it, which I always appreciate. But the key takeaway is that the information content of an event is directly tied to its probability. The less probable it is, the more information it packs.
Okay, that makes sense. But what happens when we're not talking about just one event, but a whole bunch of possible outcomes? Like imagine we're flipping a coin, there are two possible outcomes, heads or tails. How do we measure information in that kind of scenario?
That's where the concept of entropy comes into play. It's essentially a measure of the average information content, or the average uncertainty of a random variable.
So instead of looking at just one event, we're looking at the overall randomness or unpredictability of a situation.
Exactly. And just like with information content, there's a formula for calculating entropy, which takes into account the probabilities of each possible outcome.
Oh, I bet that formula is even more fun than the one for information content.
It's a bit more involved, but the idea is similar. We look at each possible outcome, consider its probability, and then kind of average it all together to get a sense of the overall uncertainty.
Got it. So higher entropy means more uncertainty, more randomness, right?
Exactly. Now here's where it gets really cool. The entropy also tells us the theoretical minimum number of bits those zeros, and ones that computers use needed to represent information from that source.
Really? So there's a direct connection between this abstract concept of entropy and the very practical world of digital data.
Absolutely. The choice of the base of the logarithm determines the units of entropy. Base 2 gives you bits, which is what we're usually dealing with in computers. But you can also use other bases like E, the natural logarithm, which gives you units called nats.
Nats. Sounds like something out of a nature documentary.
Haha, right. But the point is, entropy gives us a fundamental limit on how efficiently we can compress data. The higher the entropy, the more bits we need on average to represent the information without losing any of it.
So this is like the ultimate compression limit. Like no matter how clever our algorithms get, we can't squeeze the information into fewer bits than the entropy dictates.
Exactly. And the Wikipedia article gives a great example of this using letters of the alphabet.
Oh yeah, I remember that. They showed how if all the letters were equally likely, you'd need a certain number of bits per letter. But if some letters are more frequent than others, you can use clever coding schemes to use fewer bits on average.
Precisely. And it turns out that the entropy captures this perfectly. It tells us exactly how many bits we need on average, given the probabilities of each letter. The less uniform the probabilities are, the lower the entropy, and the more we can compress the information.
That's amazing. So this abstract measure of uncertainty has very real implications for how we store and transmit data efficiently.
It really does, and it highlights the deep connection between probability, information, and the digital world.
Okay, so we've covered information content and entropy. Are there any other key properties we should know about?
Yes, the information theory and overview source goes into a bit more detail about some of the key properties of both the information content function and entropy itself. For example, the information content function is what's called monotonically decreasing.
Monotonically decreasing. That sounds a bit intimidating.
It just means that as the probability of an event increases, its information content decreases, which makes sense, right? The more certain we are about something, the less new information we get when it happens.
Yeah, that makes intuitive sense.
And another important property is that the information content of an event that is certain to happen, something with a probability of 1, is 0. Which again makes sense because if we already know something is going to happen, it doesn't tell us anything new.
Right. No surprise, no information.
Exactly. And then there's the property that if we have two independent events, the information we gain from observing both of them is simply the sum of the information we gain from each one individually.
So if I learn two unrelated facts, the total information I've gained is just the information from each fact added together.
Precisely. And entropy itself also has some interesting properties. For example, it's continuous, which means that small changes in the probabilities of outcomes lead to small changes in entropy. So it's a smooth and well-behaved measure, not something that jumps around erratically.
Okay, that's good to know. It means it's a reliable way to quantify uncertainty. What else?
Well, another key property is that entropy is maximized when all the outcomes are equally likely. In other words, we have the most uncertainty when every outcome is equally possible.
So maximum randomness equals maximum entropy. Makes sense.
Right. And then there's the principle that if we increase the number of equally likely outcomes, the entropy also increases. So more possibilities, more uncertainty.
Intuitively, that makes sense. If you have a dice with 6 sides instead of just 2 like a coin, there are more possible outcomes, so more uncertainty about what you'll roll.
Exactly. And then finally, there's the property of additivity. This tells us that if we have a system made up of multiple independent parts, the entropy of the whole system is simply the sum of the entropies of the individual parts.
So it's like the information from each part just adds up to give you the total information of the system.
Right. And all of these properties together give us a really solid foundation for understanding entropy as a fundamental measure of uncertainty.
Okay, that's a lot to digest, but I think I'm starting to get a handle on this entropy thing. It's all about probabilities and randomness and uncertainty. But there's one thing that's still bugging me. If entropy is just about probabilities, does it even care about what those probabilities represent? Like, does it matter if we're talking about flipping coins, the letters in a book, or the weather patterns in a particular region?
That's a great question, and it gets to the heart of what information theory is all about. And the answer is no, entropy doesn't care about the meaning or the context of the events. It's a purely statistical measure. It only cares about the probabilities of the outcomes, not what those outcomes represent.
So whether it's heads or tails, rain or shine, the calculation is the same. It's all about the numbers.
Exactly, which is both powerful and limiting. Powerful because it gives us a universal way to quantify information regardless of its source. Limiting because it doesn't tell us anything about the meaning or the value of that information.
Makes sense. It's like a tool for measuring the raw quantity of information, but it doesn't tell us anything about the quality or the relevance of that information.
Precisely. And that's something to keep in mind as we delve deeper into the applications of information theory.
Okay, so we've laid a good foundation with information, content, and entropy. Now, I'm really curious to see how this stuff actually gets used in the real world. What are some of the applications mentioned in the outline?
Well, the first one listed is conditional entropy and mutual information. These concepts are all about looking at the relationships between different random variables.
So instead of just looking at one variable in isolation, we're now considering how variables might influence each other.
Exactly. Conditional entropy, denoted as HXY, is a way to measure the uncertainty we have about a random variable X, given that we already know the value of another random variable Y.
So it's like saying, if I know this piece of information, how much does that reduce my uncertainty about something else?
Precisely. And the key idea is that knowing something about Y should generally reduce our uncertainty about X. The partaa.pdf document provides the inequality H, XY, HX, to express this formally.
Oh, and inequality. That takes me back to high school math class.
Don't worry, it's not as scary as it sounds. It basically just means that the conditional entropy of X given Y is always less than or equal to the entropy of X alone. In simpler terms, knowing something about Y can only decrease our uncertainty about X or, at worst, leave it unchanged. It can't make our uncertainty greater.
That makes intuitive sense. Like if I know it's raining outside, I'm less uncertain about whether I need an umbrella than if I have no information about the weather.
Precisely. That's a perfect example. And then there's the related concept that the entropy of two random variables considered together, called the joint entropy and denoted as HXY, is always less than or equal to the sum of their individual entropies, HX plus HY.
So if we know something about the relationship between two variables, that knowledge reduces the overall uncertainty compared to considering them completely separately.
Exactly. And we achieve equality only when X and Y are completely independent, meaning knowing one tells us nothing about the other.
Okay, so conditional entropy is all about how knowledge of one variable can reduce our uncertainty about another. What about this mutual information thing?
Mutual information, denoted as I, XY, goes a step further and quantifies the amount of information that one random variable contains about another. It's essentially a measure of how much our uncertainty about one variable decreases when we know the value of the other.
So it's like a measure of how much those two variables talk to each other, information-wise.
Exactly. It captures the amount of shared information between them. And the really cool thing is that this mutual information is symmetrical.
Symmetrical. You mean the information X has about Y is the same as the information Y has about X?
Precisely. It might seem counterintuitive, but the math works out that way. If knowing X helps you predict Y, then knowing Y will help you predict X to the same extent. The reduction in uncertainty is mutual.
Wow, that's fascinating. It's like they're sharing a secret language that only they understand.
In a way, yes. And this concept of mutual information has a lot of practical applications. For example, in inferring gene regulatory networks, it can help us identify which genes are interacting with each other based on their expression patterns.
So we can use information theory to decode the communication networks inside living cells. That's incredible.
It is, and it highlights just how versatile and powerful these concepts are.
Okay, so we've covered conditional entropy and mutual information. What other applications does this outline have in store for us?
Well, next up, we have a connection to fields you might not immediately associate with information theory: reliability engineering and quality control.
Reliability engineering and quality control. Not exactly the first things that come to mind when I think about information and entropy. How do those fit in?
It might seem surprising, but these fields actually rely heavily on probability and statistics. In reliability engineering, we're often interested in predicting when systems or components might fail. This involves modeling the time to failure using probability distributions.
So, like, what's the probability that a certain component will fail within a given time period?
Exactly. And by understanding these probabilities, engineers can design systems that are more robust and reliable. Now, how do you think information theory could be relevant in this context?
Well, if we think about an unexpected failure, something that happens with very low probability, it's kind of like receiving a lot of new information. It could indicate a design flaw or a problem that needs to be addressed.
That's a great insight. You're essentially saying that these rare failures carry more information because they're so surprising. And by analyzing these failures through the lens of information theory, we might gain insights into how to improve the system's reliability.
Okay, so it's about extracting valuable information from those unlikely events. What about quality control? How does that tie into all of this?
In quality control, we're concerned with making sure that manufactured products meet certain standards. Often, it's not feasible to inspect every single item. Instead, we use statistical sampling methods based on probability.
So we inspect a small sample of the products and use that information to infer the quality of the whole batch.
Exactly. And information theory can help us design optimal sampling strategies, like how many samples do we need to inspect to gain enough information about the overall quality of the batch?
So it's about finding that sweet spot between minimizing the inspection costs and maximizing the information we get about the product quality.
Precisely. And it all comes back to understanding probability and information.
All right, that makes sense. Now, what's next on our application tour?
Okay, the next one is system simulation, which is another area where probability plays a huge role.
System simulation, like those computer models they use to predict the weather or simulate traffic flow.
Exactly. And when we're dealing with complex systems, there's often a lot of randomness involved. Think about things like the arrival of customers at a store or the fluctuations in the stock market.
Right, those are definitely not predictable events.
And to accurately model these systems, we need to incorporate randomness into our simulations. This is done using random number generators, which are governed by probability distributions.
So we're basically using probability to mimic the randomness of the real world in our computer models.
Precisely. And information theory can then help us analyze the output of these simulations, like how much information are we actually gaining about the real system from our simulated data.
So it's not just about building the model and running it, it's also about quantifying how much useful information we're getting from it.
Exactly. And that can guide us in refining our simulations and making more informed decisions based on the results.
Okay, that's really interesting. Now, what's next? This outline is packed with applications.
The next one is a bit more technical, but it takes us back to our discussion on data compression. It's called Craft's inequality, and it's all about the limits of building efficient codes.
Craft's inequality. Okay, that sounds a bit intimidating.
Don't worry, we'll break it down. Remember how we talked about using variable length codes to compress data more efficiently?
Yeah, the idea of giving shorter codes to more frequent symbols and longer codes to less frequent ones.
Right. Well, Craft's inequality gives us a mathematical rule for determining which sets of code word lengths are even possible. It essentially ensures that we can decode the message without any ambiguity.
So, like, if we make one code too short, it might mess up the decoding of other symbols.
Exactly. And Craft's inequality prevents us from running into those kinds of problems. It's like a constraint that ensures we can build codes that are both efficient and decodable.
Okay, that makes sense. It's like a set of rules for building a good code. And then the outline mentions something called the first main theorem of information theory. What's that all about?
That's a big one. It's often called Shannon's source coding theorem, and it basically formalizes the idea that the entropy of a source sets a fundamental limit on how much we can compress the data from that source without losing any information.
So entropy is not just a measure of uncertainty, it's also a measure of compressibility.
Exactly. And this theorem tells us that in the idealized scenario, we can achieve an average code word length equal to the entropy. Now, in practice, we usually can't reach that exact limit because we're restricted to using integer code word lengths.
Right, computers work with bits, which are whole units.
But the theorem also tells us that we can get arbitrarily close to that entropy limit by encoding longer and longer sequences of symbols together. So it's a really powerful result that shows how entropy dictates the ultimate efficiency of data compression.
Wow, that's pretty mind-blowing. It's like entropy is the ultimate code breaker, telling us just how much we can squeeze the information without losing anything. Okay, what's next on our list of applications?
Okay, the next one is cryptography, which is all about keeping information secret and secure.
Cryptography. Now, that's something I'm definitely interested in. How does information theory play a role in that?
You might think that higher entropy, meaning more randomness, would always lead to better security. And in many cases, it does. A truly random secret key is much harder to guess than one that follows a predictable pattern.
Right, because with more randomness, there are more possibilities for the key, so it's harder to crack.
But it turns out that entropy alone doesn't tell the whole story. The distribution of that randomness also matters. If some keys are more likely to be chosen than others, even if the overall entropy is high, An attacker could focus their efforts on those more probable keys.
So even if the key space is large, if there's a bias in how keys are chosen, it could create a weakness.
Precisely. And that's where the concept of guesswork comes in, which takes into account the probability distribution of the keys. The Study Smarter article on information theory has a great example of a one-time pad with a non-uniform key distribution.
A one-time pad is supposed to be unbreakable, right?
In theory, yes. But if the key isn't truly random, meaning some parts are more predictable than others, it can introduce vulnerabilities.
So it's not just about having enough randomness, but also about making sure that randomness is distributed evenly across all the possible keys.
Exactly. And information theory helps us understand and quantify these subtleties of cryptographic security.
Okay, that's fascinating.
Yep.
So entropy is important, but it's not the only factor to consider in cryptography.
Right. It's a complex field with lots of nuances, but information theory provides a powerful framework for analyzing and improving security.
This is really eye-opening. What other areas have we got left to explore?
Okay, next up is machine learning, which is all about building algorithms that can learn from data and make predictions.
Machine learning. It's such a hot topic these days. I'm curious to see how information theory fits in there.
Well, one way to think about machine learning is as a process of reducing uncertainty. We're trying to build models that can accurately predict unknown outcomes based on the data they've been trained on.
So the more the model learns, the less uncertain it is about the world.
Exactly. And since entropy is our fundamental measure of uncertainty, it naturally finds its way into many machine learning algorithms.
Can you give an example?
Sure, one common application is in decision tree learning. In a decision tree, we're essentially asking a series of questions to classify data into different categories.
Like those flowcharts where you answer yes or no questions to arrive at an answer.
Exactly. And at each step, we want to choose the question that provides the most information, that reduces our uncertainty the most. And to do that, we use a concept called information gain, which is directly related to the change in entropy.
So we're essentially using entropy to guide the learning process and make the most informative decisions at each step.
Precisely. And this is just one example. Information theory pops up all over the field of machine learning, helping us build better algorithms and understand the limits of learning from data.
That's amazing. Who knew that entropy could be so useful in teaching machines how to learn?
It really highlights the power of these fundamental concepts. Now, for our final application, we're going to take a bit of a leap from the digital world into the realm of physics, specifically statistical physics.
Statistical physics, that sounds like a pretty big jump.
It might seem like a distant field, but there's a deep and elegant connection between information theory and statistical physics. And it all starts with the famous equation, Boltzmann's equation.
Oh, I've heard of that one. It's like engraved on every physicist's heart.
Something like that. It's a fundamental equation that relates the thermodynamic entropy of a physical system to the number of possible microscopic configurations or microstates of that system.
So the more ways you can arrange the microscopic components of a system while still maintaining the same macroscopic appearance, the higher the entropy.
Exactly. And this thermodynamic entropy is often interpreted as a measure of disorder or randomness. The more microstates, the more disordered the system is.
Okay, I remember learning about that in my physics class. But how does this connect to Shannon's information entropy? They seem like totally different concepts.
They do, but there's a beautiful link. Shannon's information entropy can be seen as a measure of how much information we're missing about the exact microstate of a system,
Right.
given that we only know its macroscopic properties.
So, like, if we see a glass of water at room temperature, we know its macroscopic state, but we don't know the exact positions and velocities of all the individual water molecules.
Precisely. And the more possible microstates that are consistent with that macroscopic observation, the higher the information entropy. It's like a measure of our ignorance about the detailed microscopic arrangement.
So in a way, information entropy is about the missing information needed to fully specify the system's state.
Exactly. And this connection goes even deeper. In some contexts, Shannon information is actually referred to as negative entropy. It's like the opposite of disorder or randomness. And from a thermodynamic perspective, the total information of a closed system can only decrease over time, which is related to the second law of thermodynamics.
Wow, so information and entropy are intimately linked to the very laws that govern the universe.
It really highlights the profound nature of these concepts.
Okay, this has been a whirlwind tour of information theory and its applications. My brain is definitely full, but in a good way. Before we wrap up, I'm curious, is there anything else mentioned in the outline that we haven't touched on yet?
Actually, there are a couple of more advanced topics. The outline mentions typical sequences and their connection to entropy through the method of types and Sanoff's theorem.
Okay, typical sequences and Sanoff's theorem. Those sound pretty intense.
They are a bit more technical, but the basic idea is that these concepts help us analyze the statistical behavior of long sequences of outcomes from a random source. A typical sequence is one where the observed frequencies of the different symbols are close to their true underlying probabilities as determined by the source's entropy.
So, like, if we flip a coin a million times, we expect to see roughly half heads and half tails, right?
Exactly. And that would be considered a typical sequence. Now, Sanoff's theorem tells us that sequences that deviate significantly from this typical behavior become exponentially rarer as the length of the sequence increases.
So the more data we have, the less likely we are to see anything that significantly violates the probabilities dictated by the entropy.
Precisely. It's like a law of large numbers for information theory. And this has implications for things like data compression and coding theory.
Wow, that's really interesting. Okay, and what about the last item on the outline, the Legendre transformation and the Gertner-Ellis theorem? Those sound super advanced.
They are. Those are tools from probability theory and statistical mechanics that are used to analyze the probabilities of rare events, what are called large deviations. These tools allow us to study how systems behave when they stray far from their typical or average behavior.
So, like those black swan events that are highly unlikely but can have huge consequences.
Exactly. And these tools can be used to quantify the likelihood of those rare events and understand how they affect the overall behavior of complex systems.
Okay, my brain is officially overflowing with information, but in the best possible way. This has been an amazing deep dive into information theory.
It really is a fascinating and incredibly versatile field.
I have to say, I came into this thinking it would be all about dry math and abstract concepts. But you've shown just how much this stuff is connected to the real world and how it impacts everything from data compression and cryptography to machine learning and even physics.
It's a truly foundational theory with its fingers in a lot of different pies.
Well, dear listener, we hope you've enjoyed this exploration of information theory as much as we have. If you're feeling inspired to continue this journey of knowledge discovery, we encourage you to subscribe to the All Sorts podcast on YouTube, where you'll find a whole universe of past deep dives waiting for you. And be sure to follow us on X, Instagram, and Threads to stay up to date on all things All Sorts podcast.
And as you go about your day, take a moment to think about how the principles of information theory might be at play in the technology you use, the decisions you make, and even the way you perceive the world around you. It's a powerful lens for understanding how information shapes our reality.
Until our next deep dive, keep exploring, keep learning, and keep that spark of curiosity burning bright.